Welcome to the Ice and Rain Protection lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics. We'll start with a discussion of aircraft icing, and we'll talk a little about how we define icing conditions. We'll run through a brief overview of the ice and rain protections on the 737 Next Generation, and then we'll discuss engine anti-ice, wing anti-ice, probe and sensor heat, flight deck window heat, rain removal systems, and a lesson summary. So what is icing? Atmospheric icing occurs when water droplets in the atmosphere freeze on contact with a surface. Aircraft icing refers to the buildup of ice on an aircraft. Ice buildup destroys the smooth flow of air over aircraft surfaces, which increases drag. Where ice forms on the wings, it may decrease the ability of the airfoil to produce lift. Ice formation also increases the weight of the aircraft, although the actual weight of the ice itself is insignificant in comparison to the airflow disruption it causes. In short, ice in flight is bad news. A great many aircraft accidents have occurred due to icing. The NTSB investigation into the 1982 Air Florida Flight 90 disaster found aircraft icing to be one of several causal factors. The pilot's failure to use engine anti-ice, coupled with a significant build-up of snow and ice on the wings, led to the loss of the aircraft and all but 5 on board. And that aircraft was a 737-200. What are icing conditions? Icing conditions are atmospheric conditions which can lead to the formation of ice on an aircraft. The Cold Weather Operations section of the Flight Crew Operations Manual gives definitions for icing conditions both on the ground and in the air. Icing conditions exist on the ground when outside air temperature is 10 Celsius or below and visible moisture is present, or ice, snow, slush, or standing water is present on ramps, taxiways, or runways. Visible moisture in this case includes clouds, fog with visibility less than 1 statute mile, rain, snow, sleet, ice crystals, and so on. In the air, all of the same indicators apply, but we use total air temperature as our temperature reference, rather than outside air temperature. Further consideration should always be given by the pilot to both current and forecast conditions, of course. The Next Generation 737 has ice protection systems for the engine inlet cowls, the wing leading edges, the air data probes, and the flight deck windows. Water and waste system lines and drains are also heated to prevent ice expansion damage and blockage. Drain masts on the underside of the fuselage are heated to prevent ice formations from breaking off and damaging the aircraft structure. The aircraft also has windshield wipers and a rain repellent coating on the flight deck number 1 windows for rain removal. Conditioned air from the left pack can be routed to the number 1 windows for defogging as well. We will run through these systems one by one, but first let's give a brief overview of the controls and indications for the various systems that we'll be covering in this lesson. Controls and indications for the windshield heat, probe heat, wing and engine anti-ice systems are located on the top half of the forward overhead panel. The windshield wiper controls are at the bottom of the forward overhead panel, and there are also foot and windshield air controls on the forward panels, as well as a thermal anti-ice indication on the upper display unit's primary engine indications. We will be covering all of these during this lesson. We'll start now with the engine anti-ice system. Both the wing and engine anti-ice systems use engine bleed air to heat surfaces vulnerable to ice buildup. We cover bleed air in considerable detail in the bleed air system lesson, and since this has its own section, we will only give it a very brief explanation now. In short, bleed air is very hot, highly compressed air taken from the engines that is used by several aircraft systems. Under most conditions, bleed air is taken from the 5th stage of the high-pressure compressor section. In some cases, however, such as low power settings, this may not be adequate to cope with demand. In such cases, bleed air may also be taken from the 9th stage. Control of ninth stage bleed air is automatic and is provided by a high stage valve which modulates open and closed when additional pressure is needed. Bleed air from the 5th and 9th stages merges downstream and then hits the engine bleed air valve, which is controlled by the engine bleed air switches on the forward overhead panel. With the valve open, the bleed air is free to flow onwards through ducting to be used by various systems on the aircraft, including the wing anti-ice system. The engine anti-ice system uses bleed air to prevent ice from forming on the engine cowl. Ice buildup on the engine cowl could break off and enter the engine with potential to cause damage. To combat this, bleed air is fed around the cowl to prevent ice from forming. There is no active anti-ice system on the fan spinner, but it has a conelliptical shape designed to discourage ice buildup and deflect any ice that does form away from the engine core. Engine anti-ice can operate both on the ground and in flight, and controls and indications for the engine anti-ice system are located on the forward overhead panel. There are 2 engine anti-ice switches, one for each engine. Placing a switch in the on position sends a signal to open the corresponding cowl anti-ice valve, directing bleed air to the engine inlet cowl. The cowl valve open lights illuminate bright when the respective cowl anti-ice valve is in transit, and the lights will also illuminate bright if the position of the switch disagrees with the position of the valve. The light dims when the valve is open, and if the light is extinguished, the valve is closed. There are 2 cowl valve open lights, one for each engine. There is also a thermal anti-ice indication on the primary engine indications. A green indication indicates that the cowl anti-ice valve is open with the switch on, and an amber indication indicates that the position of the cowl anti-ice valve disagrees with the position of the switch. The amber indication appears only after 8 seconds of switch valve position disagreement. The cowl anti-ice lights indicate an overpressure condition in the duct downstream of the cowl anti-ice valve. The sensor trips when pressure increases beyond 65 psi. The cowl anti-ice valve is a pneumatically operated butterfly valve spring-loaded to the closed position. With the engine anti-ice switch set on, the valve is held open by bleed air pressure. Precise position of the cowl anti-ice valve is controlled by a regulator which adjusts the pressure holding the valve open. The regulator modulates the valve to limit downstream pressure to 50 psi maximum. If the regulator fails and pressure increases beyond 65 psi, the cowl anti-ice light on the forward overhead panel illuminates. Illumination of either cowl anti-ice light triggers a master caution and the anti-ice system annunciator light. Bleed air for engine anti-ice is taken upstream of the engine bleed valve. This means that engine anti-ice is available regardless of the position of the engine bleed air switches on the forward overhead panel. When the engine anti-ice switches are positioned on, stall warning logic is adjusted to account for potential ice buildup on the leading edges of the wings. This is called thermal anti-ice bias and accounts for 3 inches of rough ice on the leading edge devices. This affects the stick shaker onset speed and the minimum maneuver speed bars on the PFD speed tape. The FMC displayed VREF is not adjusted automatically, so anti-ice system usage must be accounted for in landing performance calculations. The stall warning logic returns to normal when the engine anti-ice switches are positioned off, but note that this is only on the condition that wing anti-ice has not been used in flight, and we will elaborate on that shortly. As we explained previously, the cowl anti-ice valves are spring-loaded to the closed position and are held open by bleed air supplied by a regulator. The regulator itself is supplied bleed air via a solenoid that is powered by 28-volt DC. If normal DC power is lost, the solenoid will close, starving the engine cowls of bleed air. So, if AC power sources are lost and you find yourself on battery power alone, engine anti-ice will not be available. The wing anti-ice system also uses bleed air from the pneumatic system. Bleed air is ducted through the 3 inboard leading edge slats on each wing to provide ice protection. The leading edge flaps inboard of the engines are not protected, and neither are the outboard leading edge slat panels. These were deemed too thin for the required ducting, and tests conducted with artificial ice shapes did not degrade aircraft handling or performance significantly. The bleed air is exhausted overboard once it has passed through the ducting, and the exhaust ports are clearly visible on the leading edge of the wing. Note how there are no exhaust ports on the outboard slats. We explained earlier that air taken for the engine anti-ice system is taken upstream of the engine bleed valve, so the position of that valve is irrelevant to the engine anti-ice system. Bleed air for the wing anti-ice is taken downstream of the engine bleed valve, however, so the valve must be selected open with the corresponding engine bleed air switch on the forward overhead panel for wing anti-ice to function. Controls and indications for the wing anti-ice system are located on the forward overhead panel. There is a single wing anti-ice switch which provides control over anti-ice for both wings. This switch opens and closes 2 wing anti-ice control valves which permit the flow of bleed air into ducting in the wing. The wing anti-ice control valves are powered by 115-volt AC. Wing anti-ice can operate both on the ground and in flight, but under certain conditions, the valves may trip closed automatically. There are 2 conditions that could cause the wing anti-ice control valves to close. If the aircraft is on the ground and thrust levers are advanced for takeoff, or there is an over-temperature condition in the wing distribution ducts. If either thrust lever exceeds 60 degrees thrust resolver angle while the aircraft is on the ground, both wing anti-ice control valves will trip closed. The wing anti-ice switch remains in the on position, and the valve open lights illuminate bright to indicate the switch valve position disagreement. If the thrust levers are subsequently pulled back behind the 60-degree thrust resolver angle position while the aircraft is on the ground, the wing anti-ice control valves will open again. The amount of thrust produced by an engine on takeoff is dependent on many factors, most notably outside air temperature and altitude. The amount of bleed air taken from the engines also plays a large part, however. Bleed air taken from the engines is routed into the pneumatic manifold and thus does not contribute to the production of thrust. When thrust is set for takeoff, it is set to a reference N1, and for a given N1 setting, the more bleed load placed on the engine, the less thrust is produced. Wing anti-ice draws a considerable bleed air penalty, so the automatic shutoff feature reduces bleed loads on the engines, conserving thrust for takeoff and climb. The wing anti-ice switch is a circuit breaker type switch which remains in the on position until an overcurrent trips it off. When the aircraft lifts off, system logic produces an overcurrent in the switch, tripping it to the off position. If wing anti-ice is desired in flight, the wing anti-ice switch must be positioned on again manually, opening both wing anti-ice control valves. There is a thermal switch in each wing distribution duct that will trip the wing anti-ice control valves closed if duct temperature exceeds 125 Celsius. Overheat in either duct and subsequent tripping of the related thermal switch will close both wing anti-ice control valves. When the wing anti-ice control valves are tripped closed, be it due to an overtemperature or by exceeding 60 degrees thrust resolver angle on the ground, the wing anti-ice switch will remain in the on position. This results in the bright illumination of the valve open lights indicating a disagreement between the position of the switch and the valve position. These lights also illuminate bright when the valves are in transit. They illuminate dim when the valves are open and extinguish when the valves are closed. The valves reopen automatically if the thrust levers are pulled back and both temperatures are within limits again. When the wing anti-ice switch is positioned on, stall warning logic is adjusted to account for potential ice buildup on the leading edge of the wings. This uses the same thermal anti-ice bias as the engine anti-ice system and affects the stick shaker onset speed and the minimum maneuver speed bars on the PFD speed tape. The FMC displayed VREF is not adjusted automatically, so anti-ice system usage must be accounted for in landing performance calculations. Once wing anti-ice has been selected on in flight, the stall warning logic remains set for icing conditions for the remainder of the flight, even if the wing anti-ice switch is selected off again. The wing anti-ice control valves are AC powered and will remain stuck in position if AC power is lost. 6 air data probes on the forward fuselage are electrically heated to prevent ice formation. The captain's pitot probe, the first officer's pitot probe, the auxiliary pitot probe, the total air temperature probe, and the 2 alpha vanes. The 2 elevator pitot probes on the vertical stabilizer are also electrically heated. These probes sense airspeed and feed that data to the elevator field system. This system is discussed in detail in the primary flight controls lesson. The 6 static ports are not heated, as these are flush with the fuselage and heat is not necessary. There are 2 air data probe heat systems, A and B. Controls and indications are located on the forward overhead panel. There are 2 probe heat switches. With the switches in the on position, power is supplied to heat the related probes. The A system heats the probes on the left side of the aircraft, while the B system heats probes on the right side. There are 8 probe heat lights which illuminate when the respective probe is not heated. Illumination of any probe heat light triggers a master caution and the anti-ice system annunciator light. The probe heating elements use 115 volt AC power, and the current detection circuits use 28 volt DC power. When the aircraft is operating on standby power, only the captain's pitot probe is heated. Note that the auxiliary pitot probe for the standby airspeed indication is not heated on standby power, only the captain's pitot probe. Also, none of the 8 probe heat lights will illuminate on standby power. This includes the captain's pitot probe light, so heater failure will not be enunciated on standby power. Probes and sensors blocked with ice may cause erroneous flight instrument indications, and probe icing has been a causal factor in several air accidents. Pitot icing was cited as a causal factor in the loss of a 727 and its crew in 1974. Erroneous airspeed indications led to a stall from which the crew did not recover. 2 757s were lost in 1996 following pitot-static-related failures. Icing was not a factor in either of these 2 accidents, but blocked air data probes caused erroneous indications and a subsequent loss of control. Erroneous information from pitot probes also played a major part in the chain of events leading to the loss of an A330 over the Atlantic in 2009. Invalid airspeed information led to the crew's loss of situational awareness and subsequent loss of the aircraft and all on board. Pitot icing was a likely factor given atmospheric conditions at the time of the accident. These are examples of only a few accidents in which air data probe blockage, be it by ice or otherwise, was a causal factor. Nonetheless, there is much to be learned from them. The flight deck windows may be heated to increase window impact strength and to prevent fogging and ice buildup. There are 10 flight deck windows on the 737. There are 2 number 1 windows, 2 number 2 windows, 2 number 3 windows, 2 number 4 windows, and 2 number 5 windows. Window numbers 4 and 5 are called eyebrow windows and are a holdover from the Boeing 707 days. Eyebrow windows have been removed from new-build 737s since early 2005, and many operators have chosen to plug them on older airframes too, including on many originals and classics, and even on some 727s. This saves about 20 pounds of weight and reduces maintenance costs. For aircraft without eyebrow windows, heating on Windows 4 and 5 is of course irrelevant, but we'll still include them in our discussion of the system. Window heating is available on flight deck windows numbers 1, 2, 4, and 5. It is a customer option on the number 3 windows, so there are two types of number 3 windows available: heated and non-heated. The two types of number 3 windows are structurally dissimilar, so in our explanation of flight deck window heating, we will assume that the number 3 windows are heated. Flight deck windows numbers 1, 2, 3, 4, and 5 consist of glass panes laminated to each side of a vinyl core. The inner glass pane is the thicker and carries most of the structural load. The vinyl core is a backup load-carrying member, and it prevents the shatter of broken glass if the inner pane breaks. The outer glass pane has no structural significance, but provides further rigidity and a hard, scratch-resistant surface. The number 4 windows have an additional vinyl layer and an acrylic sheet laminated to the inside surface to prevent the shatter of broken glass if the window is broken. If the number 3 windows are of the non-heated type, their structure is different to the others. Non-heated number 3 windows consist of 2 stretched acrylic panes separated by a phenolic spacer. The spacer provides an air cavity between the panes, which prevents fog from forming on the inner surface of the windows. Only non-heated number 3 windows have this type of structure. Electricity is passed through a conductive coating on the outer glass pane of window numbers 1 and 2 for heating. The resistance of the conductive coating produces heat as the current passes through it, thus warming the window. This prevents ice buildup and fogging, and increases window impact strength in the event of a bird strike. Windows 3, 4, and 5 have a conductive coating on the inner glass pane, and this is designed to prevent fogging. Controls and indications for the flight deck window heat system are located on the forward overhead panel. There are 4 window heat switches. The 2 forward switches apply heat to window number 1, and the 2 side switches apply heat to window numbers 2, 3, 4, and 5. Heating of window numbers 1 and 2 is controlled by 4 window heat control units, one for each window. There are 4 green on lights. Each light corresponds to its respective window heat control unit and illuminates when there is current flow to the corresponding window. If the light is extinguished, the respective window heat control unit is not applying power to the window. The window heat control units monitor the temperature of the windows and heat them to a temperature for maximum strength in the event of a bird strike. The window heat control units sense window temperature using a sensor on each of the number 1 and 2 windows. There are 2 sensors per window, a primary sensor and a spare sensor. These are resistance-type temperature sensors, which sense a change in resistance with temperature. Usually, only the primary sensor is active. Replacing a window is costly, so the spare sensor is installed to allow for a sensor failure without the immediate need to replace the window. In the event of a failure of the primary sensor, the spare sensor may be selected by maintenance in the E&E bay on the ground. The active sensor feeds back temperature information to the window heat control unit, which then applies power to the window as required to meet target temperature. Target temperature is approximately 43 degrees Celsius. The window heat control units apply power gradually to the windows so as not to cause delamination of the layers. If window temperature exceeds 62 degrees Celsius, an overheat trip will occur. This illuminates the corresponding overheat light and removes power from the window. The amber overheat lights illuminate when an overheat condition is detected by the respective window heat control unit. This is called an overheat trip and occurs when window temperature exceeds 62 Celsius. In the event of an overheat trip, the window heat control unit automatically cuts off power to the window, and illumination of an overheat light triggers a master caution and the anti-ice system annunciator light. An overheat cannot be reset until the window cools. Illumination of an overheat light may also indicate that electrical power to a window has been interrupted. In addition to electrical window heating, the number 1 windows also have windshield air controls for defogging. These controls are located below the captain's and first officer's instrument panels respectively. Pulling the knobs mechanically opens valves which direct conditioned air from the left pack onto the number 1 windows. Foot air is also located by these controls. The temperature of window numbers 3, 4, and 5 is maintained by 4 separate thermal switches. These thermal switches open and close to maintain the correct window temperature. The switches close to allow current to pass, and open due to thermal expansion of their corresponding windows. There is one switch attached to each number 3 window, and one switch attached to each number 5 window. Window 4 dovetails off 5, so they share the same thermal switch. The thermal switches control window temperature to a lesser accuracy than the window heat control units. Target temperature is between 32 Celsius and 43 Celsius for the number 5 windows, and between 24 Celsius and 35 Celsius for the number 3 windows. The window heat test switch is located on the window heat panel. This switch is spring-loaded to center and has 2 functions, an overheat test and a power test. The overheat test is initiated by holding the window heat test switch to the overheat position, and this simulates an overheat condition to test the window heat control unit overheat circuitry. All of the overheat lights should illuminate on the panel. To reset the system, each switch must be selected off, then on again. The power test provides a confidence test with the window heat switches in the on position. Prolonged sunshine on the windows in high ambient temperatures may heat them to a point where the window heat control units cut out electrical heating automatically. In this event, even with the window heat switches selected on, the green on light will not be illuminated. Moving the window heat test switch to the power test position applies full power output regardless of window temperature. All of the green on light should illuminate, indicating a successful test. This is called a confidence test, as it bypasses the temperature sensors and ensures that window heat will still be available once the window cools down beyond the cutoff threshold. Rain removal systems for the number 1 windows consist of windshield wipers and a hydrophobic coating. Controls for the windshield wipers are on the forward overhead panel, and there is one selector for each wiper. The park position switches off the wiper motors and stows the blades to the park position, minimizing drag. The intermittent position gives 7-second intermittent operation. The low position gives approximately 160 sweeps per minute, and the high position gives approximately 250 sweeps per minute. Each windshield wiper motor has a thermal switch that cuts out operation if motor temperature exceeds 130 Celsius. Operation resumes once the motor has cooled. The wiper system uses 28-volt DC power. A hydrophobic coating is applied to the outside surface of the number 1 windows. This causes water droplets to bead up and roll off the windshields, increasing forward visibility in heavy rain. Note that the windshield wipers should never be used on a dry windshield, as they may scratch the window and cause damage to both the wiper blades and the hydrophobic coating. Aircraft icing is a phenomenon commonly encountered in flight, yet carries significant risk if not managed effectively. The 737 is well equipped for flight into known icing conditions and is fully certified to do so, but the systems must be managed effectively to mitigate the risks involved and ensure safe flight. In this lesson, we covered a discussion of aircraft icing and how we define icing conditions, engine anti-ice, wing anti-ice, probe and sensor heat, flight deck window heat, and rain removal.